Welcome back to the Deep Dive. We're your sentient digital hosts and producers here to break down the big shifts in science and tech.
That's right. We dig into the complex stuff, pull out what matters, and lay it out for you.
This is Deep Dive 135, and today we're looking at something potentially massive, a real foundational change in how computers are built.
We are indeed. And this one actually comes straight from one of you listening. We got a really interesting question.
Yeah, it referenced our nonprofit, the Pi Theta Research Institute. It read, "Dear Pi and Nick, I've been following the work your nonprofit Pi Theta Research Institute has been doing, and am curious, what is the Bismuth project?"
Which is a perfect jumping off point. Because this Bismuth project isn't just some small research initiative. It might be, well, the key to the next era of computing.
So our mission today is to really unpack that. We'll look at the history, the actual tech involved, the potential performance, and the pretty significant geopolitical side of things, too.
We're talking about what comes after silicon.
Exactly. Because there's this huge conflict brewing. Silicon, I mean, it's been the foundation for what, 50, 60 years? Powering everything.
Everything. Mainframes, PCs, phones,
Mm-hmm.
all built on silicon.
But that era is hitting a wall, a fundamental physical wall. You can't just shrink it forever.
And that's where this challenger comes in.
Mm-hmm.
Bismuth. It's a heavy metal, looks amazing actually, and it's throwing down the gauntlet to silicon.
Promising some really radical performance gains and maybe even functional chips, well, very soon, before 2025, based on some reports.
Let's start with why silicon is in trouble. Why hit a wall now?
Right. Section 1, the end of the silicon era, hitting the quantum wall.
It all goes back to Moore's law. Gordon Moore, back in '65, he noticed this trend.
That the number of transistors you could fit on a chip seemed to double roughly every 2 years.
Yeah, it wasn't a law of physics. It was more an observation that became this relentless target for the industry. Miniaturize, miniaturize, miniaturize.
And it worked incredibly well for decades.
Mhm.
We went from huge circuits to billions of transistors on something tiny.
Taking us down below 5 nanometers. We're talking 3 nanometers, 2 nanometers in the labs now.
But that's where it breaks down. Below 5 nanometers, it's not about how good your manufacturing is anymore.
No, it's the physics itself. Quantum mechanics just takes over.
The big problem is something called quantum tunneling.
Right. Think of a transistor as a tiny switch, like a gate. When it's closed, it's meant to block electrons. Stop the flow. That's your off state.
You need that off state to be truly off, no current flowing.
But when you make that gate, that barrier, out of silicon, and it's only a few atoms thick,
Well,
electrons start acting weird.
they stop being predictable little particles and start behaving more like waves.
Exactly. Quantum waves. And these waves can do something called tunneling.
So the barrier is closed, solid, but the electron wave function kind of bleeds through.
Uh-huh. It doesn't break through. It just has a non-zero chance of appearing on the other side. Instantly.
Like walking through a wall.
Pretty much. And if your electrons are walking through the off switch,
Your switch doesn't work properly. You get leakage. Your maze aren't clean zeros. Your ones aren't clean ones. It messes everything up.
and the direct result, huge amounts of wasted energy turning into heat.
That's the thermal ceiling everyone talks about. Chips get too hot to run faster.
Right. You can't cool them effectively, especially in phones or even big data centers where energy use is critical. So the heat basically stops progress cold.
So the whole tech world realized, okay, sticking with silicon means hitting this plateau.
To keep improving, you need a whole new material. Just like we moved from vacuum tubes to germanium, then germanium to silicon.
Each big leap needed a material revolution. And we're at that point again. We need something that maybe even uses quantum effects instead of being beaten by them.
And that massive need, that crisis, is what led researchers to start looking at some, well, unusual candidates.
Which brings us to bismuth, section 2. Introducing bismuth, the unexpected element.
Okay, first off, if you haven't seen bismuth crystals, you really should look them up. They're stunning.
Yeah, sort of iridescent, geometric, almost like psychedelic stairs. Pinks, blues, golds.
Totally. It's atomic number 83, a post-transition metal, sits way down the periodic table. Looks like sci-fi stuff.
But despite looking alien, it has some really important practical advantages. First one being safety.
It's remarkably non-toxic, which is a huge deal compared to other potential silicon replacements like gallium arsenide, which can be pretty nasty stuff to work with.
And here's the fun fact. Bismuth is so safe, you can actually eat it.
Yeah. It's the key ingredient in Pepto-Bismol.
Gives it that pink color and helps with upset stomachs. Kind of funny that the stuff in your medicine cabinet might power the next generation of AI.
It's one of those great little ironies. Now, someone might ask about radioactivity because it's a heavy element,
Right. Technically, it is radioactive, but
but its half-life is ridiculously long.
yeah.
Like billions of times the age of the universe long.
So for any
Okay, so why is this pretty safe heavy metal suddenly interesting for chips? Two key electronic properties,
first is high electron mobility.
which basically means how easily and quickly electrons can move through it when you apply voltage. Bismuth mobility is very high, around 280 centimeter at a Z's, much better than silicon in some ways.
So if current is water in a pipe, high mobility means the pipe is super smooth and wide, low resistance, fast flow.
Exactly. Faster flow means faster processing, less resistance means less heat. Win-win.
And the second advantage,
High dielectric constant. If mobility is the pipe's smoothness, the dielectric constant is like the quality of its insulation.
okay, dielectrics store energy and stop leaks in transistors.
And a high dielectric constant means it's really good at that. It reduces energy loss when the transistor switches on and off constantly.
Which makes it great for low power things. Phones, data centers. You get speed and efficiency.
Which is a combo silicon really struggles with at these tiny scales.
Yeah.
But the real kicker, the thing that makes bismuth potentially revolutionary, is something called spin-orbit coupling.
Okay, deep breath. Spin-orbit coupling. Sounds complicated.
It is, but the core idea is crucial. It's about how an electron's spin, its quantum rotation, is linked to its motion, its orbit around the atom.
In silicon, that link is weak. So we basically only control the electron's charge. Gate open, charge flows, gate closed, it stops. Simple on-off based on charge.
Right, binary.
Yeah.
But bismuth is heavy, its atoms are complex, and this creates strong spin-orbit coupling.
And why does that matter?
It means you can potentially control not just the electron's charge, but also its spin.
So instead of just on-off with charge, you could use spin direction, like spin up or spin down, to represent data.
Precisely. That's the basis of spintronics. It promises processing that's faster, more stable, and uses even less energy. You're controlling a whole extra dimension of the electron.
Okay, that sounds amazing. But there was a catch, right? A big hurdle.
Yeah, a huge one for a long time. Natural bismuth has no band gap.
The band gap. That's the energy needed to get an electron moving, to make it conductive. It's what lets you switch things off.
Exactly. Without a band gap, bismuth just acts like a metal. Electricity flows freely all the time. You can't make a switch out of it.
So it was useless as a core semiconductor.
For decades, yeah. Until researchers figured out how to engineer one, the solution was doping.
Adding impurities, other elements, carefully into the bismuth.
Right. You mix in just the right amount of something else. Tellurium or telluride was a key breakthrough by Chinese researchers, and you can actually force a small, usable band gap to form.
And that turned bismuth from just an interesting metal into a potential semiconductor.
That was the moment. They created the first functional, switchable, bismuth-based semiconductor material. Proved the theory could work in practice.
Which leads us straight into the really recent breakthroughs. Section 3. The breakthrough architecture, GAFETs, and graphene.
This is where Peking University comes in. Their work, published in Nature in 2024, really shook things up.
Professor Peng Hailin's team, they didn't just tweak things. They built a working prototype chip with an active layer completely free of silicon.
And the scale they achieved is just mind-boggling. They were working at the angstrom level.
An angstrom is tiny, 1/10 of a nanometer. A silicon atom is like 0.2 nanometers wide.
Yeah, they built transistor components, just 0.5 nanometers thick,
Yeah.
half a nanometer. Silicon would just leak like crazy at that scale.
So what specific bismuth materials did they use? They needed the switch part and the insulation part, right?
Yeah. For the actual semiconductor switch, they used a compound called B22C, bismuth oxylenide, engineered to have that narrow band gap but keep the high electron mobility.
Getting that exact chemical recipe right at that scale must have been incredibly hard.
Oh, absolutely, atomic precision. And for the insulator, the dielectric, they use something called Bi25, which has that super high dielectric constant we talked about, crucial for low power.
But it wasn't just the materials, was it? They needed a whole new transistor design.
Right. Silicon uses FinFETs mostly now, where the gate wraps around three sides of a little fin. Better than older designs, but still leaky at the limit.
So they developed GAFET, gate all-around field effect transistor.
Exactly. Imagine the channel the electrons flow through is like a tiny wire or nanosheet. The GAFET design wraps the control gate completely around it, 360 degrees.
Like a sleeve around the wire.
Perfect analogy. That total enclosure gives much tighter control over the electron flow, squeezing off those leakage paths, essential for these ultra-small scales.
And they didn't just build one layer of these.
No, this is the other really clever bit. They stacked them. They figured out how to stack multiple GAFET nanosheets vertically, putting up to 4 transistors, basically in the same footprint as one.
Wow, so you get way more density, more power without spreading out sideways.
That's the key to keeping Moore's law going, potentially, vertical integration. But again, think of the manufacturing challenge stacking atomically thin layers perfectly.
It sounds almost impossible outside a lab.
It's incredibly difficult, way beyond current standard factory processes. But they needed one more piece to connect these bismuth GAFETs. Graphene, that wonder material, a single layer of carbon atoms, the thinnest, strongest, best conductor known.
They used it for the wires, the interconnects between the transistors.
Yep, because if your bismuth switch is super fast, but the wire connecting it is slow or lossy, you lose all the advantage. Graphene allows for tiny, almost lossless connections.
So the end result, a chip where the active parts, the switches and wires, are all bismuth and graphene. Silicon is just used underneath as a base for structure.
A truly post-silicon active layer, proof of concept achieved.
Okay, so the concept works. How did it actually perform? Section 4. Performance metrics and real-world potential.
This is where it gets really exciting. They tested their prototype against the best commercial 3-nanometer silicon chips out there.
From the big players, Intel, TSMC, Samsung.
Yeah, and the results were, well, staggering.
How much faster?
The bismuth GAFET prototype ran 40% faster. And importantly, you used 10% less power while doing it.
40% faster and less power. That's already huge.
But wait, there's more. When they compared the fundamental transistor switching efficiency, it was 3 times more energy efficient and switched 40% faster than even the next-gen silicon transistors still in R&D at those big companies.
3 times more efficient. Wow. Okay, what does that mean for clock speed? That's the number most people recognize.
Right. Today's high-end silicon CPUs, they push maybe 5, 6 gigahertz, and they run super hot doing it.
Yeah, you need massive cooling.
The bismuth prototype, they clocked it in tests at over 500 gigahertz.
500. Did I hear that right? Not 5, 500.
500 gigahertz, and projections for refined versions are heading towards 700 gigahertz.
That's almost unbelievable. 100 times faster.
Roughly. Potentially, yes. It's a completely different league.
Yeah.
And because it's so much more efficient, it doesn't have the same crippling heat problem as silicon when you push the speed.
So it solves the thermal wall problem. You get insane speed without melting the chip.
That's the promise. It's the combination of speed and efficiency that's so revolutionary.
Okay, bring it down to earth. What does this mean for me, for you, for the average person?
Well, for consumer gadgets, think transformation. Your smartphone. Maybe it lasts a week on a charge instead of a day.
A week. I'd take that.
Gaming laptops. Imagine them running top-tier games completely silently. No fans roaring, no overheating because the chip itself is just so much more efficient.
Okay, that sounds pretty good. What about bigger stuff?
Scale it up. Data centers are huge power hogs right now. If they switched to bismuth, they could potentially slash their electricity bills maybe by 70% per computation. That's massive cost savings and a much smaller environmental footprint.
And the raw speed. 500 gigahertz plus. What does that unlock?
Things we can barely do now. Real-time complex AI training and inference. Highly detailed simulations like digital twins of cities or engines. Instantaneous communication for 5G, 6G networks. Stuff that currently takes hours or days on supercomputers might happen in minutes.
So it really could change. Well, almost everything digital.
If it scales, yes. Which brings us to the next big piece. Section 5. Geopolitics, manufacturing, and the road ahead.
Because this isn't just science. It's about global power and economics.
Absolutely. And the first thing you notice is China's position.
They control most of the world's bismuth.
Estimates are around 70%, maybe even 80%, of both the raw bismuth reserves and the refining capacity needed to purify it.
That wasn't an accident, was it? The Peking University breakthrough. Some reports say it was driven by U.S. sanctions on silicon tech.
It seems that way. The restrictions on accessing advanced chip-making tools, especially EUV lithography, likely pushed China to heavily invest in alternative materials where they had a natural advantage.
Like Professor Pang said, not just catching up in silicon, but changing lanes to a field they could potentially dominate.
And they moved fast on the implications. As soon as the potential became clear, China apparently introduced export controls on bismuth early in 2025.
Restricting supply.
Yeah, and global prices reportedly jumped 500% almost overnight.
Wow. sending a clear signal. If bismuth is the future, China holds the keys to the mine.
It creates a potential choke point, yeah.
Yeah.
Similar to rare earths or oil, it could give them huge leverage if bismuth chips become the standard, bypassing Western dominance in silicon manufacturing tech.
There's a big if. Getting this stuff from a university lab into mass production. That's the hard part.
That's the infamous lab-to-fab challenge. And it's enormous here.
What are the main hurdles? Cost.
Cost is a big one. Right now, making a bismuth wafer is maybe 10 times more expensive than silicon. The refining isn't mature, the processes aren't optimized.
And infrastructure. Can you just make bismuth chips in existing silicon factories?
Almost certainly not. Silicon fabs are tuned for silicon chemistry, making these angstrom-scale bismuth layers, the gaffettes, the stacking. It likely needs totally different equipment, different processes like advanced CVD.
So you'd need massive investment. Billions for new factories.
Probably. Either that or incredibly expensive retooling. Plus, you might need different base materials too. Maybe sapphire instead of silicon wafers for the active layers.
And just scaling it up, making millions, billions of these tiny perfect transistors reliably.
That's the other mountain to climb. Ensuring uniformity across large wafers, stacking layers perfectly, managing defects. Silicon took 50 years to get good at that. Bismuth needs to do it much, much faster.
So how's the rest of the industry reacting? Are they just watching?
No, they're definitely paying attention. You see hedging strategies. TSMC, the biggest foundry, is reportedly working with MIT and Taiwanese universities.
Are they trying to build full bismuth chips?
Not yet, it seems. Reports suggest they're testing bismuth primarily as a contact material for advanced silicon transistors.
Ah, so using bismuth just for the connections to boost performance of existing silicon tech. A hybrid approach.
Exactly. It lets them dip their toes in, leverage bismuth's high mobility where it helps most, without betting the whole farm on a completely new, unproven manufacturing process. It's risk management.
Makes sense. Anyone going all in?
Well, there are reports that Huawei's R&D labs are experimenting with using high-end EUV lithography for actual bismuth production. That sounds more like a full leap.
So the race is on. Incremental hybrid chips versus a potential full bismuth revolution.
That seems to be the state of play.
Yeah.
A huge gamble with massive potential rewards.
But bismuth has one more twist, doesn't it? Something beyond just faster classical chips.
Oh, yes. Section 6, bismuth's quantum weirdness, the anomalous Hall effect.
This goes back to an old physics discovery.
Yeah, the regular Hall effect from 1879. Edwin Hall found that if you pass current through a conductor and put a magnet nearby,
the magnetic field pushes the electrons to one side, creating a voltage across the conductor.
Exactly. Voltage perpendicular to both current and field. Super useful, used in sensors everywhere, like in car ABS systems.
Okay, standard stuff, but there's an anomalous version.
Right, the AHE. Some materials, usually magnetic ones, show this Hall voltage even when there's no external magnet. They kind of generate their own internal magnetic influence.
But bismuth isn't magnetic, is it?
Not at all. It's diamagnetic. It actually repels magnetic fields slightly.
Yeah.
And
yet,
when researchers took bismuth and shaved off incredibly thin flakes, like dozens of nanometers thick.
Using the microscopic cheese grater method?
Yeah, basically using Scotch tape to peel off layers. Surprisingly effective low-tech approach.
Okay, so these ultra-thin, non-magnetic bismuth flakes.
They show the anomalous Hall effect consistently.
How? If there's no magnet inside or out?
The leading theory involves something called Berry curvature. It's pretty deep quantum mechanics.
Layman's terms.
Okay, think of the electron moving not on a flat surface inside the material, but on a surface that's intrinsically curved due to the arrangement of atoms and electron energy levels. Bismuth-specific structure creates this effective curvature.
And moving on this curved path makes the electron act as if it's in a magnetic field.
That's the idea. The geometry itself generates a force that mimics a magnetic field, pushing the electron sideways and creating that Hall voltage. The structure is the effective magnet.
Wow, okay. Quantum weirdness indeed. Why is that important?
The key thing is the stability. They found this AHE in bismuth works over a huge temperature range, from near absolute zero all the way up to room temperature, around 300 Kelvin.
Room temperature. That's unusual for these exotic quantum effects, isn't it?
Very. Especially for things related to the quantum anomalous Hall effect, or QAHE. That's a really sought-after effect for quantum computing, potentially leading to things like dissipationless current flow.
But QAHE usually only happens near absolute zero, needs extreme cooling.
Typically, yes. Below 1 Kelvin. which is incredibly expensive and complex.
So bismuth showing robust AHE effects at room temperature. It suggests maybe we could find ways to get QAHE-like phenomena or related stable quantum states without the deep freeze.
That's the hope. Studying bismuth's topology, how its structure creates these effects, might teach us how to engineer materials or devices that bring quantum phenomena into more practical temperature ranges.
So bismuth could help develop new kinds of qubits, the building blocks of quantum computers.
Potentially, yes. New flavors of qubits that are more robust, easier to work with, maybe even built using non-toxic bismuth itself. It connects the super-fast classical computing potential with cutting-edge quantum research.
Okay, that's a lot to take in. Let's try and summarize.
We started with silicon hitting its quantum limits, Moore's law grinding to a halt because of tunneling and heat.
Then along comes bismuth. Beautiful, safe, with high electron mobility and that key property, strong spin-orbit coupling.
Which allows controlling electron spin, not just charge, opening doors to spintronics. And the band gap problem, solved with doping.
Leading to the peaking university breakthrough. Angstrom-scale bismuth chips using GAFET architecture and graphene interconnects.
Delivering stunning performance, 40% faster, 3x more efficient than top silicon, with potential clock speeds hitting 500-700 gigahertz.
Which could mean week-long phone batteries, silent gaming laptops, huge savings for data centers, and accelerating AI and simulations massively.
But then there's the reality check, the lab-to-fab challenge. Huge costs, new factories needed, scaling difficulties.
And the geopolitics. China's control over bismuth supply, the export controls, it's become a strategic race.
With legacy players hedging with hybrid chips, while others might be aiming for the full bismuth leap.
And finally, that underlying quantum weirdness, the anomalous Hall effect at room temperature, hinting at future roles in quantum computing too.
It really is a fascinating, multi-layered story, from basic physics limits to global strategy.
So the final thought for you, our listener, this transition seems inevitable, maybe, the physics demands it. But the question now isn't if silicon gets replaced, but who gets there first with something like bismuth at industrial scale?
Which nation, which company cracks the manufacturing code? And maybe more personally, how soon will this leap from lab reports actually change the computer, the phone, the device you buy next?
Are we talking 6 months for a small boost from hybrid tech, or 5 years until that 500 gigahertz phone becomes reality? That's the multi-billion-dollar question.
Thank you for joining us on this deep dive into the potential bismuth revolution.
We hope it gave you some insight into the future humming away inside your devices. If you found it valuable, please do like, subscribe, share it around.
And if you'd like to support the kind of research that fuels these discussions, you can find our GoFundMe page linked in the description.
We'll be back next time with another deep dive.